Did somebody do the right function or something? Anyway, it says, honor your father and mother so that you may live long in the land the Lord your God is giving you. So obviously this comes from the 10 Commandments, and I just thought of this verse, and I don't know, I don't want to sound preachy or whatever, but I've just been thinking about the quarantine being lifted and stuff like that, and even just reacting and how we all react is like, we don't want to go the opposite route and kind of go crazy and be rebellious or things like that. And just like I've kind of talked about, like you guys are getting older and that sense of independence gets stronger and more powerful. And at the same time, you have this kind of like responsibility still living at home to honor your parents and respect them and things like that. But I just think the cool thing about this verse is that there's a promise. It says, so that you may live the Lord your God has given you. So there's a blessing. And it's actually, maybe you've already heard it, but it's the only commandment that has a blessing tied to it. So you guys have this opportunity, especially while you're still in your parents' house, to receive that blessing and to kind of build up the deserving that blessing. So anyway, I just wanted to encourage you to do that, even though I guess I kind of think about it too, because you guys have had to have been home so much more than you're used to, and like just being around your parents more than you're used to. And so it can get hard and people can get tense and stuff like that, and just whatever. So, but just be extra aware of whether you're honoring your parents or not, because the Lord's watching, and that's something that he looks at and he blesses. So anyway, and I have kind of a quick story. I think if I've shared it with you, I'm sorry, but I think I shared I know I shared that I had wanted to go to school for law, and then I just got to a place where I was like, no, that's not right for me. And then I wanted to switch colleges, and I wanted to go to Trinity, which is a Christian college. But in going to Trinity, at first I wanted to go and become like a biblical studies and youth ministry major. And my parents were like, you're a woman. You're not going to have very many job choices. And I didn't want to be a pastor per se, but just involved in youth ministry and stuff like that. They're like, they just felt like you're not going to have a lot of opportunities to really make that your paying career. And I was ticked. I was not happy, because I'm like, I'm in college, and I felt like they weren't supporting that decision. And so in my heart, I wanted to be rebellious and find a way okay, because they were helping me pay for college. So I was kind of beholden to them, to honor them in that way. And so I was in my mind, I'm all trying to figure out, well, is there a way I could pay for college myself and just do this on my own and, branch off and be done with their support? But I decided to honor them, and instead, I just prayed through it and asked God, to show me what to do. And I shared the story about how God led me into education. And so I honored them, and I chose education, and that was all God showing me that that's what I should do. And in doing so, I've been able to be involved in youth ministry my whole adult life. I've always been part of the youth groups and working as a youth leader, and been able to teach the Bible in that way. I get to share verses with you guys and kind of do devotions that way. And so God has actually allowed me to do that. And it didn't have to be my quote unquote career that I get paid to do. But it also has brought other opportunities where I was able to be a missionary in China because I had a teaching degree. In order to do that, I had to have some other cover kind of job in order to get there. And to protect us, we needed to have a job that was legit in the Chinese government's eyes. And so anyway, God has used it, and I've been able to use teaching and having that certification in a lot of different respects. And it's given me a lot of different opportunities that I wouldn't have had otherwise. So I can see, and I've looked back and seen how just honoring my parents, I also protected my relationship with my parents. They were okay with me switching to a Christian college, and that was fine with them. And I was able to get out of that experience a lot. And I've been able to use that. So anyway, when you have those opportunities and that independent side of you wants to rise up and rebel, work to fight against that, because God will bless it. The blessing might not come immediately. You might look at it later on in life and be able to realize how God used that. So anyway, just my thought for today. Alrighty, so moving on. What we're going to do today is I'm going to attach kind of a name to some of the theorems that we've learned this past week. And the Bob Jones lesson does that, and it kind of will maybe give us a reference point, as well as we're going to apply them to kind of decide, well, can we use these theorems to like help us find out if lines are actually parallel or if things are actually proportional. So I'm just going to review some of these theorems. So this is actually theorem 53. We already talked about it. I already presented it. But the Bob Jones book calls it the Sidesplitter Theorem. So basically, it says, again, if a line is drawn through two sides of a triangle parallel to the third side, then it divides the two sides proportionately. So that side splitter, it splits the sides up. So remember, we're not dividing it evenly necessarily, it divides it proportionately. So if one side has a ratio of 1 to 3, then the other side is going to have a ratio of 1 to 3, whatever the different values might be. So we can look at AB is to BD, so the left side divided into two parts is to AC is to CE. Okay, now remember, we have to keep those corresponding parts in mind, that if it's the short part compared to the long part, we need to, on the other side, compare short to long. So you always have to keep in mind the corresponding parts. So that's a side splitter theorem. We, in our book, had theorem 53. And then the corollary to the side splitter theorem. So corollary 53.2 is what our book called it. And that was where we had corresponding segments cut off on two transversals by a series of parallels are proportional. Okay, so we've seen something like this a long time ago too, but we looked at equal segments. That's a slightly different case, but so we can see that if we travel from one side of the parallels to the other, from one transversal to the other, we have corresponding segments that would be proportionate. So we can say something like this. If we have a series of parallel lines, we can say A is to 12 as 4 is to 10. So if you notice, I just traveled across through the parallels to the other side to get to a corresponding segment on the other transversal. Or 12 is to B as 10 is to 8. So we can also stay on the same side of the parallel. And as long as we go in the same direction in the other transversal, so 12 and B, I went from above to below. And then if I go across the parallels to the other transversal, I can go above and below. So 12 is to B as 10 is to 8. So you have to follow the same kind of pattern, if you will. And then we also had A is to B. So this is the one I asked you guys to do when we did this lesson. Can we do it again? A is to B as what? What would we fill in?
4 is to 8.
4 is to 8. So again, following the same pattern. A and 4, we could actually split it around and we could say A is to 4 as B is to 8. That would be a legal way as well. That would be the alternation transformation. Okay. All right, so that also then yesterday, in yesterday's lesson, hopefully if you got cut off, you had a chance to watch the rest of the video. I try to keep it kind of short and simple. But the theorem that we learned was theorem 55, and that is called the triangle angle bisector theorem, in other words. Your book calls it theorem 55. And it describes the bisector of an interior angle of a triangle divides the opposite side internally, so inside, into two segments or that have the same ratio as the other two sides. So we have a diagram kind of that looks like this. That line that goes down through the middle is the angle bisector. So you notice that that line that's unmarked bisects the vertex angle. And when it bisects the vertex angle, and that's the key, that line has to be the angle bisector. If it's not the angle bisector, then C is to D is not going to be the same as A is to B. Okay, the proportionate relationship won't exist. But if that line is the angle bisector, then we have a proportionate relationship. That is that the short side of one of like the triangle is to the short segment of that third side is to the longer segment of the side is to the longer segment that's divided. Okay, so we can switch this proportion around in the same ways that we could in our other transformations. Okay, so remember, transformations still apply in these proportions because they're proportions. But generally speaking, we start with this bisector theorem as stating it as A over B. So like the side to the side is as to the two segments are, okay? So, but we can transform it using our rules of transformations as well. Okay, so we're gonna do a little bit of practice, and we're gonna write some proportions as indicated by the theorems that we've learned. Okay, so remember theorem 53 is the side splitter theorem. Are the boys being too loud in the background? Can you guys hear them? They're not bothering you? Okay, if they get too loud, let me know, because they can go outside and play. So Isaiah's room is just not too far away. So, okay, so the side splitter theorem would be something that could apply to a diagram that looks like that. I have to get out of this section for a second. I just have to move things around. Sorry, when it's in presentation mode, it won't let me use my cursor to move things around. Okay. All right, so our first directions say write the proportions indicated by the side splitter theorem. So we want to pick out there's actually several we could write. We just have to make sure we follow an appropriate pattern. So what's a proportion that I could write that would follow the side splitter theorem?
4 over 2 equals 7 over x.
Yeah, 4 over 2 equals 7 over x. Okay, so I'm going to go over and go ahead and write that. Okay, so 4 over 2 equals 7 over x. Now, if we want to go ahead and find the value of that missing segment, what would we do? Okay, this is the part that I want to become like second nature, that you don't have to think hard about. So how are we going to solve for x when we have a proportion?
Something like 4 over 7 equals 2 over x, right?
That's a transformation. Okay, that's another proportion. Yep. So another.
Wouldn't we cross multiply and get like 4 over x equals 14?
Okay, not 4 over x, 4x. So when we multiply, we get 4x equals the product of these two, which is 14. Okay, and so then we go ahead and we divide by 4. Okay, so x is going to equal whatever that is simplified. So what does that simplify to?
2 1/2.
Okay, 2 1/2. So it first goes to 7 halves, and well, not 2 1/2. 7 halves is, because 2 times 2 is 4. So we can go up to 3. 2 times 3 is 6. So we get 3 1/2. You're close. Okay, so when we have a triangle like this, and we have a line that's splitting the two opposite sides into segments, when those lines are parallel, we have a proportionate relationship. So if we need to know the length of that missing side, it's going to be 3 1/2 if the proportion is 2 to 4 on one side, or I mean the ratio is 2 to 4 on one side. Okay, so that would be one where we use the side splitter theorem. But just remember this, there are different ways you could write that same proportion and it would still be valid. Okay, so Mark gave us, he said 4 over 7 equals 2 over x. Okay, and remember, you can see it too, because you still get 4x equals 14. This would have been 4 over 7, that would have been alternation. Okay, you could have done it as like, well, what's another one we could have done? This is part of what you have to do today, so I'll just go a little further, because it did say write proportions indicated by this. What's another example of another proportion that would be correct, keeping within the bounds of the side splitter theorem and transformations that we have?
Seven over 2 equals 4 over x.
7 over 2. Okay, so let's see. How are you getting that then?
Well, I mean, if there's 3 numbers and the x, couldn't we just interchange any of them?
Okay, let's see. You said 7 over 2 equals 4 over x?
Mm-hmm.
Okay. All right, well, let's take a look at this. If we do this, we have 7x equals 8. We divide. Does x equal the same thing?
Nope.
Yeah, it doesn't. Okay, so that that doesn't necessarily, like, because I'm trying to let's see, 7 to 4. Let's see, 2 over x. Something went wrong here. You didn't use one of the transformations, I don't think. So, because what happened is you weren't comparing corresponding sides anymore. Okay, because the proportionate relationship isn't from the side that's 2 to 7. Okay, the 2 has the proportionate relationship to the 4. Okay, or it has the proportionate relationship to the x. Okay, so I'm glad you said that, Jacob. All right, let's go on to the corollary to the side splitter theorem. Okay, so the corollary just has to do with parallel lines and transversals instead. So that's just a little bit of a difference. And so let's go ahead and let's write some proportions that would be true for this one. So the first part is to write some proportions. Okay. So what would be some proportions that would be valid?
Four.
I couldn't hear you completely.
Yeah, no, I changed my mind.
Oh, okay. Anybody else want to try? How about Alyssa or Gilbert? One of you guys? Somebody we haven't heard from? Can you hear me, Alyssa?
Yeah, I can hear you.
Okay. Do you have an idea of what proportion we could write for letter C?
Is this the one I did yesterday in class?
It's not the same as what we did yesterday in class. It's more like 2 days ago, I think.
What do you do?
I don't have my book.
Oh, can you see the screen? I'm just talking about
No,
the screen.
I can't see the screen.
Oh, okay. Can the rest of you see my screen?
Yup,
I can only see,
just like normal.
I can see you, Mark, and Izzy. That's what I see.
Really?
Yeah.
So you can't see my screen share. Hold on a second. Let me just redo it. That's kind of weird. Let's see what comes through. Otherwise, I can draw it on the board. Can you see it now?
Yeah.
Okay. All right. So here, do you see the diagram on the right with the parallel lines and the transversals?
Mhm.
Okay. All right. So what I'm trying to do is I'm trying to find a proportion that would be true for this corollary. So we're talking about letter C. So this is the corollary to the side splitter theorem. What's a proportion that would be true about these values?
4. Well, I don't know.
Give it a try. It's okay. If you're wrong, you're wrong.
4x is equal to 15, or 4x is proportionate to 15.
Okay, that's the way that you don't want to go. Okay, we don't want to cross the parallel lines and cross the transversal. So to go from 4x to 15, you crossed not only like the transversals, but you crossed the parallel lines. If we can think of it like that, that's a no-no. Okay, we can just cross a parallel, and still keep the proportion, or we can just cross the transversals and keep the proportion true. So for maybe visual people, that'll help. So don't cross.
Suggestion.
Yes.
Could
So would it be
email
4
your
over
mom when
3x over
the video comes
3x
out because you're kind of breaking
equals
up.
5x over 15?
Okay, hold on a second. Jacob or Gilbert's trying to tell me something. Gilbert, can you repeat?
Could you email my mom when the video goes out? Because I'm breaking up. My end's breaking up. So
Okay, so when the
sorry.
video goes on Facebook, you want me to let your mom?
Yeah.
Okay,
Yeah.
so you're just
I'm
gonna
like,
close out then?
yeah.
Okay.
Yeah.
Yep, I will email your mom and you can watch it later. That's fine.
All right. Thank you.
You're welcome. Okay. All right, Izzy, go ahead. I'm sorry. Izzy, can you say what you said it before again?
Yeah, would it be 4x over 3x equals 5x over 15x?
Yes, that would work. Okay, so as long as I keep the same two like related segments on one side of one transversal and then the same two related segments on the other side of the transversal, then those can be proportionate. So one option could be 4x over 3x equals, it was 5x over 15. Okay. What's another option that would keep the relationship proportionate? Can somebody think of another option?
Could you go? Never mind.
It's okay. Okay. The one other thing that you can immediately do that I want you to be able to see is that you can go directly kind of horizontally over just the transversals and go through the parallel lines without crossing them. So I could also write 4x over 5x equals, as long as I go from the same side to the other side, 3x over 15. And notice, if I do that, my cross products still end up the same, 4x and 15, 4x and 15, okay? And that's what's really important about it, is that's keeping that same ratio of similarity, okay? So we'll go ahead and we'll solve one of these, because the second part is going to be to solve for x, okay? Now, before I solve for x on this, it's actually helpful for me to simplify a little bit, okay? Because this problem has something we could simplify. A couple things that we could simplify. Sorry, my cat's meowing. He loves going outside, and Joseph, our neighbor boy, just got picked up and they went outside, and my cat's all sad because he didn't get to go too. So if you look here, we can simplify. So here we set up a proportion, but the next step would be to simplify. So I can cancel out those x's, and I also can cancel out here. 5 goes into both 5 and 15, so I can change this to a 1 and this to a 3. So I have a new ratio here. 4 over 3 equals 1 over, let's see, 1 over 3, okay? But, oh wait, they wanted us, let's see, 450x squared. This one is different. I'm sorry, I just totally, okay, this one has a quadratic. Sorry, never mind. Hold on a second. So we'll do 4x to 3x equals, I guess you can't do it this way with the figures that they gave here. Because obviously if you just saw, the ratios didn't work out. Okay. So instead, the better way to do this to solve, because we do want to solve for x. Sorry, I jumped the gun on that. We want to do 4x times 15 equals 3x times 5x. Okay. So we would do 4x times 15, and 4 times 15 is 60. So it'll be 60x equals, let's see, 15x squared. And then we can go ahead and we could write like a, an equation that has, like, if you guys remember from algebra, we can pull it into a quadratic equation. So I would minus 60x and minus 60x. And so 0 would equal 15x squared minus 60x minus 0. So then what we would want to do is our next step is that we would factor this, okay? And so we would do something like, if you remember factoring, and we would find out what the two factors would be. So we'd have to find factors of like 3x and 5x, and it would be like minus, and probably it's going to have to be minus on both of those. It kind of depends. So I'm not going to take the time to solve this whole one. I guess I forgot that this is going to be an x squared, and we don't have any problems this difficult. So I'm not going to take the time to finish this up, but this is the idea of how you'd solve it. You'd set up an equation and you go ahead and solve for x, but this is quadratics, so it's going to have two answers, okay? But anyway, so the whole idea is the proportions. And that's what I really want you to see, is that with this corollary to the Sidesplitter theorem, is that we have to set up our proportions carefully. And then when we have an unknown, we can go ahead, set up an equation, and solve for our unknown. But I'm not going to finish this because this is really kind of beyond. I just didn't catch that example. I pulled off the internet, but it has the quadratics, and we don't need to go into that. So what we do need to go into for our homework, though, is the problems that look like these. So these ones say finish the proportions and then choose to solve one for x. Okay, these ones aren't going to have quadratics in them. So we need to finish the proportions. That's one of the things it's going to ask you to do. So it's going to give you a pattern to start with, and you've got to finish it. So if I have, and this is a variation of the Sidesplitter theorem, and I have 20 over 8, how can, like, what other ratio do I have to write? What would that force the other side of the proportion to be? Okay, if 20 over 8, now notice 20 is like the full length of the one side.
Would it be 2 1/2?
Well, I'm not sure, I don't want the answer. What we want to do is like, okay, I'm not sure for x right now. What I'm asking for is to finish the proportion. So the proportion needs its second side, like its second fraction. So A, here we've got 20 over 8. And so we've got this kind of like sideways thing going on here. Oops, like this. And then we have our parallel lines are these. So these two. And we know that this full length here is 20, and the small length right here is 8. And then I know this is x and this is 6. Okay, so if I choose the ratio, the first ratio, to be 20 over 8, how am I going to set up a second ratio and set it equal to using the x and the 6? There's a little application that you got to fit into here.
Can you say what you just said? Because it broke up.
Sure. So if I use 20, which is the full length of that side, let me go ahead and stop the share so you guys can see the board big. If I use 20 for the full length of the side instead, and then I use, it's the longer of the two sections, and then I have to compare it to this side. Well, how do I get the full length of this side? That's got to be my numerator. I have to start it with the full length. So how do I get the full length of the other side of the triangle? Yeah.
Well, if the lines are, I don't know, wouldn't it be 6 on both sides?
Not necessarily. It could be. We haven't solved the proportion yet to know. But how do I show the full length of this? If I know one segment is x and the other segment is 6, what is the full length? It's going to be an algebraic expression.
6x. 6 over x.
That's if we were multiplying it. To get a length of something, we don't multiply. It's like if you're using a ruler. If I know this section and I know this section, what do I do to get the full section?
6 plus x.
The full length is 6 plus x. Okay, so on the top, we're going to put 6 plus x because this was the full length, and now I've got to compare it to the full length. Now, 8 was the longer. Let me screen share again so you can see the original diagram. Okay, so our 8. No, 8 was the shorter one. My diagram's just off. Okay, so 8 was the shorter one. And which one is the shorter one on the bottom? Look at the diagram on the screen. Which one is it going to compare to?
6 would be the shorter one.
6. Okay, so this should be 6 as the denominator. All right, so we had our ratio was really comparing the full length to the short side in both of those. So we've got to be consistent. So then in order to solve for x, we're going to do the same thing we've been doing. We're going to cross multiply. So we have 20 times 6 equals 8 times the quantity 6 plus x. Okay, so we go ahead and simplify. 120 equals 8 times 6. We've got to use the distributive property here, 48 plus 8x. Go ahead, keep simplifying, subtract 48. Well, okay, so it'd be 11. 10 minus 8 is 2. 11 minus 4 is 72. So equals 8x. Divide by 8. And we get x equals 9. Okay? So when we set up the proportion correctly, you know, the thing of it is you have to watch and just pay attention. Make sure that if they give you a full length, that you choose the full length. So the full length compared to the shorter one as the full length compared to the shorter one. You always have to follow the same pattern. Proportions are all about patterns. Okay, so make sure your eyes like visually orient to what the pattern is. That's what you want to think about. So in letter B, I had another proportion that we could create from this diagram using the Sidesplitter theorem. So if I go back, I still have the same diagram. And my proportion in letter B starts off as 6 over x. So I can also say 6 over x. So I'm comparing the short segment to the longer segment of the bottom. So how would I write the other side of the fraction? I mean, the other side of the proportion as a fraction. Now you might be thinking to yourself, okay, wait a second, I don't know the length of that second segment on that top side, but actually we do. We know the full length is 20, and we know the short length is 8.
You would subtract it, so it would be 12.
The top.
Because you know 8.
If you're trying to speak, Izzy, I can't hear you. You must be still muted.
It wouldn't it be 12? Like, I don't know, because you subtract it, wouldn't you?
I can't hear you still for some reason.
I can hear her.
So I
I
can't
can hear both of you.
all of a sudden for some reason.
I can hear you as well.
A second.
Mark's breaking up.
I can hear both.
Okay.
as well.
Mark is breaking up really bad.
I can hear you guys again. Can you hear me?
Yeah.
Yep. We could hear. I could hear Izzy and you. Mark could hear all of us, but he was breaking up.
Okay, weird. I bumped my cord and it got separated. So that's what happened to me. Anyway, so let me just go back and start this second part over again because I'm not sure where you guys got cut off. So anyway, if I have 6 over x as my first part of the proportion, I'm comparing this side to this segment to this segment. So I need to compare then this segment to this segment. Okay, so I'm going to put the 8 on the top, but what do I put on the bottom? What is the length of that segment?
6.
Oh, can you say it again, Mark?
6.
Careful. We know that the full length is 20. So if this is 8, then this just has to be 20 minus 8, right? Okay. So, yeah, you're breaking up so much, Mark, for some reason. I can't understand you. So you may have said 12 and I just couldn't understand you. I don't know.
That's what I said.
Yeah, is that what you said? I'm sorry.
Yeah.
I think I couldn't hear you because I got separated by that point. But anyway, so it should be 12 here. Okay. And and you can see what's going to happen. Watch this. This will show that both of these proportions that we set up about the same diagram is true. Okay. So 8x equals 6 times 12. 8x equals 72. Divide by 8, x still equals 9. So you can see it was really ultimately just a transformation of that proportion, right? So we still have a true proportion. Even though we were using like almost all the same numbers, we looked at it in a slightly different way, but it still corresponded. We still used corresponding sides. We just used both of the small segments compared to each other instead of like the full length compared to a part. Okay, letter B, tell if the following proportions are true. So the last thing that you're going to be asked to do is to see, or well, the second to last thing is to see if a proportion that's given is actually true. Okay, so let's look at, we've got a situation with parallel lines and two transversals. So can it be said that AB is to BC, so on the left side of this transversal, AB is to BC, as WX is to XY? Would that be true? Okay, put your hand up if you'd say yes. Okay, so if Alyssa, you can turn your video on again, that would be awesome, so I could see what you think. Okay, so if you put your hand up, you are right, okay, because we've got the short segment to the long segment compared to the short segment to the long segment. So good. Number 2, I had AB is to WX as BC is to, or wait, no. Sorry, I totally picked a different one. Number 2, AB is to WX as BC is to XY. So AB is to WX as BC is to XY. Does that follow the same pattern? Did I use corresponding sides? So AB, now remember I said it was legal to go across the transversals and through the parallels. So AB over WX, did I follow the same pattern? Did I go from then the left? Yeah, I did. I went from the left transversal through the parallel lines to the right. So AB over WX is true and equals BC over XY. Okay, so 1 and 2 were yes. Number 3, if I do AB over BC, would that be equal to XY over WX? Put your hand up if you think that would be true. Okay, yeah, I see heads shaking. No, it would not be true because I went from the, let's see, short segment on one side to the long segment, and then I did the long segment to the short segment. That doesn't work. The relationship's not the same, okay? So number 3 is a no. Number 4, BC over XY. So I go through the parallels across the transversals, BC over XY. Is that the same as WX over AB? Okay, put your hand up if you think it would be true. Okay, you're right if you kept your hands down, okay? Because I compared, okay, BC over XY, I went through the parallels from one transversal to the other. But from WX to AB, I started on the opposite side and went the other direction. That didn't keep the same pattern, okay? I can go through the parallels, but I have to start from the same side. Okay, I can't do 2 actions at once. Okay, so that's that one would be illegal. So numbers 1 and 2 were yes, 3 and 4 were no. So just be careful that you're always following the same pattern, and you should be okay. The last kind of problem that you'll need to do is you're going to check to see if lines that are intersecting, like a figure or parallel lines and transversals, check to see if they're parallel. Okay. If they're asking to see if it's parallel, what they're really asking you is, are the segments proportionate? If the segments are proportionate, we learned that by theorem 55, the Sidesplitter theorem, or 53, or by the corollary to it, that if those 2 lines are parallel, then they're going to be proportionate. Those segments will be proportionate. So that means that we've got to set up a proportion, and if it turns out to be true, then the lines are parallel. Okay? So what's one way we could set up a proportion? What would be a correct proportion?
Equals 8/14.
Okay, so Izzy, did you say 10/12 equals 8/14?
Yeah.
Okay. Oh, forgot to erase. Okay, so Izzy compared 10/12. So she stayed on the same side, which is good. And she went from top to bottom. And then she went to the other side and went top to bottom, 8/14. Okay, so she followed a true pattern. So by all practical purposes, if these numbers are right, then it would be parallel. Okay, she did the proportionate correctly. So I'm going to go ahead and cross multiply. Okay, 10 times 14, if these lines are parallel, should equal 12 times 8. Okay, well, 10 times 14, 140. 12 times 8 is 96. It's not equal. Okay, so if the equation does not balance, what does that mean about those red lines?
They're not parallel.
Yeah, so inequality indicates they're not parallel. So if this were to balance when I checked my proportion by cross multiplying, then I would say parallel. But in this case, it didn't. Okay, I'm not going to do one where it does balance. I trust that seeing this, you guys should be able to apply it to a situation where when it does balance, you'd know to say yes. Okay, so your homework is next, and that comes from a Bob Jones lesson. And I sent out an email to you guys like just before class started. I noticed I went to double check the packet to see if it was there, and for some reason, like, the first 2 pages of the lesson are there, but the homework page isn't. So anyway, I copied it and edited it, and I sent it to you in a PDF because originally I was intending it for it to be in there. But so this does not match what Friday's homework in the lesson plans that you got this week says. Okay, so ignore that. Just write this down. It's lesson 11.4, numbers 1 through 11. Okay, and there are some that have like A, B, C, D. I do want you to do all of those. A lot of these are quick. You can choose to either print it and write on it and then then take a picture, or you can just look at it on your computer screen and just make sure you label your answers correctly, like 1A, 1B, C, D, and so on, if you're just going to write on this leaf. Okay, well, that's what it's about today, just kind of practicing what we've done and applying it in some different ways.